Welcome to DCL 304, good old analog FM. Now I know in today's world, analog FM, both in the ham radio world and commercial radio, is losing favor. It's going away. But it's important to understand the basics of analog FM because D-Star, DMR, Fusion, all those fun digital voice modes are built on a foundation of analog FM. So if you take a few minutes now to understand the basics of analog FM, it's easier to understand those digital voice modes. Let's start by taking a very quick look at AM. You remember AM, sine wave carrier. So high in frequency, we don't even care about the individual sine waves. We take our low frequency audio test tone, and to superimpose it on the carrier, we use the amplitude and phase of the audio carrier, or the audio signal, to vary the power level of the RF carrier. So as this waveform is processed, the power level of the AM carrier is varied. And notice there's a mirror image of it down here. That's all AM is we vary the power level. So in AM, we say we modulate the carrier's power. That is, we vary the power of the carrier as per the intelligence or information we want to transmit. So modulation is the act of superimposing on the carrier whatever it is that we want to transmit. With FM, we start with the very same carrier. Once we modulate it, say with a complex human voice or a test tone, well, we kind of get the same thing. The reason I'm showing you this is I want you to remember there's no amplitude or power change of the carrier in FM. There's a frequency change, which is very hard to show on this scale. So here's how FM does it. Let's start on the 2 meter calling frequency for ham radio. We want to transmit a test tone, a low frequency test tone. First, let's graph the frequency of the carrier. It's actually going to just stay right here, right? Until we modulate it, it just sits here. When we modulate it, notice how the frequency swings up 2.5 kilohertz, then it comes back down, then it swings down 2.5 kilohertz, then it comes right back where it started. We literally are steering the frequency back and forth and back and forth. We make it swing back and forth to quote unquote look like the original audio signal. What if we turn the tone generator up as high as it'll go? What will change? Well, what changes is how far we swing. I have set the modulator to limit itself to 5 kilohertz either side. So we are doing 5 kilohertz deviation. We're deviating plus or minus, or actually plus and minus 5 kilohertz. What if I turn the frequency of the tone generator up? What changes? Not much. We just steer the frequency back and forth a lot faster. Now you'll notice that the input signal, the audio, is constantly changing, and the frequency of the carrier is constantly changing. It's always varying. That's a sign of an analog signal, that it never sits in the same place. And you know that it'll be between two limits, but you know what the limits are, but from 1 microsecond to the next, you don't necessarily know where the carrier is going to be unless you look at the input audio modulating frequency. Then you can predict it. All right, so in AM, we're varying the power level, and in FM, we vary the frequency. Both of these are analog modulation. Now, there's something you must know. As a ham operator, this is very important. Frequency modulation and phase modulation is just another way to obtain FM. They are both considered a form of angle modulation. Angle modulation refers to the mathematical relationships between the sine waves of the carrier. The reason I bring it up is in the FCC rules. When you see a reference to angle modulation, they're talking about FM. This is why there's so much confusion in the ham community about FM and what's legal, because when they see angle modulation, you kind of gloss over it. Well, they're actually talking about FM, but they're being very all-encompassing with their terminology. Yes, it's irritating, but I'm sorry, bureaucrats write rules that way. And the fact of the matter is, mathematically, and from a physics standpoint, it is all angle modulation. It's just so confusing when they do that. Why did I specify plus or minus 5 kilohertz? Well, it comes from commercial radio. Remember, 40 years ago, many of us hams didn't have the money to buy a ham rig, so we would get a surplus junk police radio and modify it. So naturally, we adopted the commercial standard of 5 kilohertz, even though our modulation or our deviation level isn't very strictly regulated by the FCC. It is regulated for land mobile radio. In fact, just 12 years ago, 5 kilohertz became largely illegal in the USA. As narrowbanding came along, in order to narrow everyone up with the idea they could squeeze more users into the RF spectrum. Now, this doesn't apply to everything in land mobile radio. In fact, narrowbanding only applies to VHF and UHF. The 700 and 800 megahertz band were not narrowbanded because they use analog and digital trunking technology that already makes things more efficient. And down on low band from 30 to 50 megahertz, well, that band is so quiet, nobody cares about it. Nobody uses it hardly. So narrowbanding only applied to the 4 frequency slots I'm showing you here. I doubt ham radio will ever adopt 2.5 kilohertz because we really don't have a reason to. So narrowbanding does not apply to amateur radio. And I'd like you to know that your local FM station is allowed 75 kilohertz deviation. This is for various reasons. One is to provide much better audio quality, and 2, it allows them room to transmit subcarriers that can transmit all kinds of information to your radio. Now, old analog TV used AM to send the picture, but they used a FM subcarrier that had a 25 kilohertz deviation to send the sound. Remember that for a few minutes. 25 kilohertz FM subcarrier in old analog TV. I'm going to come back to that in a moment. So what about FM in ham radio? What level of deviation is actually legal? Well, from 29 megahertz and up, there's not a lot of limit. In fact, years ago, my friends and I would build simple modulated oscillators. These were just little simple oscillators with a varactor diode in them, and a varactor is a variable capacitance component. If you fed AC signals into a varactor, or even DC, you can swing the frequency of the oscillator really well. So what we would do is we would build these little simple oscillators, feed our microphone signal into them, which makes FM. We'd feed it through an old converted tube type radio transmitter, and we would transmit on the 440 megahertz band a very wide banded FM signal of about 20 or 25 kilohertz. So what would we use for a receiver? Well, in the old analog days, TV channel 14 was 470 to 476 megahertz. We would grab an old TV and we would pad the tuner down to about 430 or 440 megahertz, and we use that as a receiver. Now, we wouldn't get a picture, but what we would get is a very economical FM receiver that could hear our wideband signal. And the audio quality was actually very impressive because, like I said, it's 25 kilohertz deviation, or about that. I mean, we didn't have instrumentation to tell us how much our deviation was. And this was legal. It's still legal. Now, as crowded as our bands are today, I don't know, you want to be a little careful about doing this. But in a lot of parts of the country, the 440 band is dead quiet. Anyway, this was a fun little experiment. It was a lot of fun to build this kind of stuff. It was back in my days of building ham radio equipment from genuine junk parts. Now, in general, we're not supposed to occupy more bandwidth than necessary. And of course, we don't send music and widebanded crap like that over the air, right? So there are some limits, but they're not super specific. So on the UHF and VHF bands, you can get away with some rather wide FM for experimental purposes, but you wouldn't want to deploy a system of hundreds of radios like this. It would be very rude to your fellow ham operators to do that. Now, below 29 megahertz, there are specific rules. First of all, there's no FM allowed on 60 meters or 30 meters. So forget it. It's just not allowed. And that's in the rules. It's very clear. But on every other frequency below 29 megahertz, there's an interesting paragraph in the rules. No, there's that term, angle modulated. No angle modulated, in other words, no FM emission may have a modulation index greater than 1 at the highest modulating frequency. Now what this does is it limits the FM signal to something no wider than a equivalent AM signal, which, by the way, AM is the widest phone or voice mode on HF. So we want to keep FM no wider than that. Well, what's a modulation index? Well, for FM, what it means is if I divide my deviation in one direction, plus or minus, by my modulation frequency, the result can't be greater than 1. So if my highest modulation frequency, for voice, it's usually 2700 hertz, but let's just say 3 kilohertz. So if my highest mod frequency is 3 kilohertz, my deviation can only be 3 kilohertz. Well, plus or minus 3 kilohertz, that's almost exactly equivalent to an AM double sideband signal. That's where the limit comes from. So FM is actually legal on HF. It's just you can't do much more than, oddly enough, the new standard, remember, in land mobile radio is 2.5 kilohertz deviation. Essentially, that's almost what we're limited to. Now, FM on HF with the noise and other signals, FM just doesn't work that well on HF anyway. So we're not losing anything by being limited. Yes, FM is a lot of fun on 10 meters, but FM is a little bit limited in that it requires a much better signal to noise ratio than single sideband does. That's it for this round. I told you it would be a quick video. I think this is my shortest one ever. If you can grasp the fundamentals I just threw at you, and again, I kept it very simple. If you understand what I just gave you, you are totally ready to tackle the super fun FM digital voice modes of C4FM, Fusion, D-Star, DMR, P25, NextEdge, all that cool stuff. And in the next video, DCL 306, we'll get started with that. I hope this was worth 14 minutes of your time. Thanks for watching, and I'll see you next time.